Thanks, Kevin. Hi, everybody, I'm Jim, one of the co-founders, as Kevin was saying. Before starting Kaleido, I was a lead architect at IBM's commercial platform for blockchain and was also a maintainer of Hyperledger Fabric. That was back in 2016 and 2017. So today I'd like to talk to you about privacy. In particular, we have a series of sessions, webinars focused on privacy. This one is on one framework called Anonymous Zether. The next one will be more of a custom-built approach. So I want to start today's session off with this landscape slide. It shows the different categories of options in terms of privacy. And specifically, how do you handle privacy when you build applications that use a blockchain? Why this is interesting is blockchain's main value has been transparency, data immutability, and distributed ledger. So a network of nodes, ideally maintained by different participants, different parties, share the same ledger. So all the transactions that get sent to the network, get processed, are all maintained by each of the nodes that are operated by each party, which means every single party has a full copy of the entire ledger. Well, I say this with the caveat that some distributed ledger technologies don't have a globally shared ledger, but they do have locally shared ledger. So the idea is always more than one party has exactly the same copy of a transaction. So there's no dispute of what transaction happened. Whether that's just bilateral or three parties sharing it, or a globally distributed network sharing the same ledger, that's up to the design of each different protocol. But because every party has access to the transaction, how do we view privacy as a requirement? It's very important for enterprise use cases to consider privacy. And it's a very wide, very big topic with a wide range of concerns and requirements. So let's take one approach at a time. On the very left-hand side is something we are all pretty familiar with. We call it boundary security. It's really APIs and authentications and data isolation with this approach. As an example, Hyperledger Fabric has channels. If you are not invited to the channel, you don't even know the channel exists because they only existed on the orderers and peer nodes of the parties that were invited to be part of the channel. Otherwise, those channels don't exist on your nodes. Or if you have a globally shared ledger like Ethereum, then you can apply API level controls if you operate the node and you want your users or your customers to have authenticated access to those nodes. Of course, if they are allowed to operate the nodes themselves, then at that point, they will have the full copy. But for the users who don't operate nodes themselves, then you can use API authentication and authorization to control what kind of information they can access from the ledger. That's very quote unquote Web 2-ish, right? It's well understood, well established approaches. Coming to the middle column, we now have a new approach that came along with DLT. We call it split of on-chain, off-chain toolkits. If you're familiar with Quorum as a protocol designed for enterprise derived from Ethereum, then you know there's a private transaction pattern called Constellation. Later on was changed to Tessera. This is very similar to that. Essentially, there are private states that are maintained by counterparties of the transaction, not to the entire network. Only the counterparties of the transaction have access to the private state, and they use private compute to manage those states and process transactions. But then they send a hash representing those transactions to the global chain, so that in the global ledger for the network, there's always a representation of every private transaction in the form of a hash. So this enforces the global order in terms of how the sequence of those private transactions. So even though you don't know the payload of those transactions, you do know there is a hash that represents the transaction. And this is essentially make off-chain processing and states, private states, work together with on-chain shared states. So that's another unique approach. And if you look at R3 Corda demo, their approach is very similar to this. And then so that there are always private states, but then there are nodes that have access to multiple party states that are involved to make sure the states are have integrity. But even if you are using a global ledger like Ethereum, you can still build a pattern using this technique. If you're familiar with Hyperledger Firefly, one operation mode of Firefly is this multi-party mode that essentially uses this pattern to use hash pinning on the chain with private messaging and transaction processing. And you can add EIP 721, 712 proof certificates into the mix so that the on-chain smart contracts can validate off-chain private states in the form of a authority approval with EIP 712 certificates. Now, coming to the right column, now we're getting to the focus of today's session, using advanced cryptography. You probably have heard of zero-knowledge proof by now. It's a very useful cryptography that proves something has been done without disclosing to you all the private inputs that were involved in the computation. But in the end, you can be convinced by using a subset of the input. They're called public input. If you have enough public input along with the proof, you can be sufficiently convinced that the calculation that was done offline in the secret place were done according to the spec, to a certain spec. And that spec in the context of zero-knowledge proof is expressed in this term called circuits. Circuit is the spec. It generates the proof. You look at the proof and use the public inputs, and you can be convinced that the calculation was done correctly. Using this, then we can do all sorts of interesting things. We can hide values. Rather than having all the values be in the clear with every transaction, we can hide them. But the problem with hiding values is, how does the smart contract validate that your transactions are valid transactions and honest transactions? Well, that's the role of zero-knowledge proof. Now, using this, we can convince the smart contract that the secret processing using the actual values are done properly, but those values are represented on-chain either as a hash or as an encrypted form. But we can still convince the smart contract that the transaction is valid. So those are the three high-level categories of approaches to privacy. So now let's focus on the one on the right-hand side of using zero-knowledge proof. Before we dive into Anonymous Zether, I want to take you through sort of a result of a survey we've been doing with our customers of the different approaches available to us when we want to use ZKP with privacy. This is not the full list, but a lot of them are either very early stage, or they are similar to some of the approaches listed here. So these are, consider this as a representative list of different approaches. So first off, Zcash. It's likely the very first blockchain with privacy, specifically for value transfer. Think of Zcash as Bitcoin, but with privacy. Why we say that is Zcash under the cover uses UTXO, which is what Bitcoin uses. It doesn't have any smart contract capability, which is also like Bitcoin. And the underlying technical components that enabled Zcash has enabled many other implementations that want to use both privacy, but also want to use ZKP in general. For example, Snark being the most popular proving system was originally constructed for Zcash purposes. And then, so Zcash is a layer one. And then we have some layer twos that have privacy built in. When we say layer twos, we typically mean layer twos for Ethereum, because you obviously need to have a layer one, and that layer one is more often than not Ethereum itself. There are many different layer twos. There are optimistic layer twos, there are ZKP-based layer twos. Aztec is the one that has built-in support for privacy. It's also based on a UTXO model. And a third category are implementations not built as protocols, but are built as smart contracts or on-chain dApps. Anonymous Zether fits in this category. So the implementation of Anonymous Zether is a combination of Solidity. Of course, it can be implemented in other smart contract languages or even for other platforms, but the main implementation that exists today is in Solidity. So it's for EVM-based deployment. The other part of Anonymous Zether are the client part to do the proving and to do the validation, if you want to do validation off-chain rather than on-chain. So those are complete systems that are sort of ready to use. You pick it up, you deploy it yourself, and then you start using it. You can also build ZKP yourself. So ZKP as a technology used to be sort of only possible with PhDs with special trainings in cryptography. But because of these tools that are listed here, more and more ZKPs are being handled by developers who can use these tools to design zero-knowledge proof circuits. You still have to have some level of understanding of how ZKP works in general, but you don't have to understand sort of the underlying math to make it work, as was the case before. The most popular are Circum by Ident3 and Socrates. They are, compared to the other two, those two are more lower level in terms of the syntax, especially Circum itself. if you look at the syntax, it's more, it's closer to the resulting arithmetic circuits than the other languages. Socrates has a slightly higher level syntax, and Aztec Noir is inspired. The syntax is inspired by Rust, so it's a pretty high level programming language. But compared to Starlight, which mostly is Solidity, the top three are relatively lower level. Starlight itself is the highest level because it uses Solidity syntax and adds a few keywords. So you express your business logic in Solidity and gets transpiled into Socrates and then uses the Socrates tool set. So using these tools, then you can design your own ZKP circuits. And in the second session, I think it's in May, we will talk about this approach, but today we'll focus on Anonymous Zether. Okay, so some of you may ask at this point, why we haven't really talked about zero-knowledge proof-based layer twos. There are so many of them, right? And a lot of them have been doing a lot of great work. Some of them launched their mainnet. Why aren't they in the list? Well, the thing is, these layer twos are based on zero-knowledge proof, but not for privacy purposes, but for scalability purposes. They upload a proof to layer one, and in order for that proof to be validated, the layer one smart contract needs all the states or all the transaction data to be able to validate that proof. So the goal is not to hide things. The goal is to use a compressed proof to represent a large amount of computation that has happened in layer two to prove that everything was done correctly in layer two. So it's for scalability. There's no privacy because after you have uploaded your data to layer one, at that point, all the transactions are in the clear. And again, Aztec is the only layer two that has privacy built in. Okay, so before we go to the next section, are there any questions from the audience? If not, let's continue.
Yeah, nothing's dropped in yet, Jim.
Sounds good. So let's talk about two different approaches to privacy on blockchain. The very first one is using an account-based model, and this is what Anonymous Zether does. Very similar to ERC-20. If you're familiar with ERC-20, you know on-chain state are organized on a per account basis, and all transactions will be settled to update the account. As soon as a transaction is finalized, the involved accounts are updated. So off of the map for the account, there's always one value that represents the latest balance for that account. When this model is used, then we typically see the on-chain state being ciphertext. It can't be commitments or hashes because, it could be hashes. Most of the hashes don't allow you to do calculation, but there is one particular hash that do allow you to do calculation. And that's Pedersen commitments. But more often than not, we see encrypted text that are used to represent the actual balance on the chain. So we're hiding the actual balance behind the encryption. And only the account owner has the ability to decipher, to recover the original balance. So, and it's usually pretty trivial to recover the balance from the ciphertext if you have the right secret key. And what we need to think about is if every time a transaction happens, the impacted account needs to be settled. How do we do that with ciphertext, right? With most of the encryption schemes, once you have done the encryption, the ciphertext itself, you can't add them. We need to find an encryption scheme that allow us to add or do subtraction on the ciphertext. That's how we can keep maintaining a single value on the chain. Well, that's exactly what the Anonymous Zether uses. In particular, it uses a scheme called encryption schemes with that are additively homomorphic. What this means is after you've done encryption on these values, you can do additions or subtractions with them. And this is very useful using the formula on the screen here. We have value 1 and value 2. Those represents, let's say value 1 represents my account's current balance. Value 2, V2 represents the increments of my balance because someone sent me a transaction to pay me something. So now the smart contracts needs to add them together. The smart contract gets the encrypted value, right? That's maintained on chain, which is encrypted V1, that's on chain. And the smart contract got the encrypted V2 in the transaction input. Now the smart contract can just add them together. The result is equivalent to when you add V1 and V2 and then do the encryption. And this means, what this means is the value you resulted from here, you can decrypt to recover the V1 and V2. And at no point, V1 or V2 was ever disclosed to the smart contract. So this is a very useful property of this particular encryption scheme if we want to use an account model. Okay, so let's come to the next design for privacy purposes on blockchain, which is using UTXOs. If you're not familiar with UTXO, just a 1-minute refresher. This is rather than using accounts so that every account has exactly one value as the balance, UTXO, think of it as a collection of coins or notes of different denominations. Every transaction produces new UTXOs that represent certain value and consumes existing UTXOs that represents value. So the on-chain state are a collection of UTXOs. Some are already spent, some are still unspent. That's why it's called unspent transaction output, UTXO. And rather than keeping track of which UTXO belongs to which account, the on-chain state is just maintaining the collection of the UTXOs. And every UTXO independently specify who's their proper owner and how much value they represent. So this is a popular design construct for many privacy solutions. And in order to hide the value, what we want to do is now we can use a commitment for the UTXO rather than putting the value in the clear. So, and the commitment usually comes in the form of a hash like this. The value, the public key of the owner plus some salt, right? This way, if the same owner owns the multiple UTXOs of the same value, then the hash will be unique because of the salt. And UTXO model is what Bitcoin uses, and many other layer one protocols. To make this solution work, if you think about it, you need a powerful off-chain client that can index every single one of the UTXOs in the system maintained by the on-chain system, so that you won't miss any UTXO that are meant for you, right? If you, let's say, somehow missed a transaction from a party that sends you $1 million, then you are not aware of that UTXO that has $1 million targeted for you, then you have your account is less than what it should be by $1 million. So you need to have a high quality client that index every single transaction, every single UTXO. And then from there, you can figure out which ones belong to you. And then from the collection of those, you can figure out what your balance is. So now the question is, with both with this input UTXO, so that these represent the UTXOs to be spent and the output UTXOs that are to be created. How do we know? We're talking about the requirement for anonymity, right? Not anonymity is not always needed. Some use cases, they need confidentiality, but they don't need anonymity, meaning we want to hide the value of each transaction, but it's okay to disclose who are transacting with who. But if anonymity is required, which means we need to hide the identity of the sender and the receiver, that means we can't disclose which input UTXOs are being consumed. Because if you did, then you have disclosed that those UTXOs belong to the sender, sender being the transaction submitter. So how we hide even the input UTXOs to be spent, we do that by the usage of nullifiers. We may not have enough time to go through exactly how nullifiers are designed, but think of it as a cryptographically secure binding to this hash. And only the owner of the public key for the UTXO is able to come up with that nullifier. So usually it's constructed as a hash of the same value, same salt, but the private key rather than the public key. When you do that, then you can validate that it's a unique hash, and it's only possible to be constructed if you know the secret key. And that's because of the property of the hashes. You have to know the pre-image to come up with the hash, not the other way around. So that's a secure way to consume UTXOs without disclosing which UTXOs you're consuming, because these are one-to-one binding between the nullifier to the UTXOs that they're consuming. And that's a very popular approach to handle anonymity in the UTXO design. And the zero-knowledge proof in this case needs to prove that the sender of the transaction actually owns the UTXO represented by the nullifiers. It also needs to demonstrate that the sum of the UTXOs for the input equals the sum of the output UTXOs. And there could be others depending on the specific requirements. I know there's a lot of information between these two slides. Want to see if there are any questions. Looks like none from the chat. So let's continue. Another interesting aspect of using a zero-knowledge proof approach is more often than not, we need new keys. So Ethereum signing keys are based on this curve, SecP 256K1. This is also true with many other layer ones or layer twos that are based on EVM, or even Bitcoin uses the same curve. Those curves are not quote unquote zero knowledge proof circuit friendly, meaning you can't use those curves inside the circuits. Zero knowledge proof circuits are basically arithmetic calculations of large numbers. That's what they end up being. And we need to find a curve that allows us to do public key cryptography inside the circuit. And most of the existing curves don't allow you to do that. So there are some curves that are specially designed so you can do key pair cryptography inside ZKP circuits. A popular one is this curve called Baby Jub Jub, and you can look at the details from this EIP description. This was designed by the IDEN3 team, which is now part of Polygon. So with this, what you can do is sometimes you need the circuit to prove that you have possession of a private key of a public key that's verifiable with a digital signature. So your public input is a digital signature, and you want to prove that the possession of the corresponding private key. That kind of proof requires you to do public key digital signing cryptography, which is not possible unless you use this kind of curve. And that's why sometimes when you use these privacy approaches that uses zero knowledge proof, you're asked to generate a new set of key pairs to handle your on-chain state rather than your Ethereum native keys. And this is why. Anonymous Zether doesn't use this particular curve. It uses BN128, which is a popular zero knowledge proof friendly curve within the EVM community. It's able to use that instead of Baby Jub Jub because it doesn't need to do this sort of calculation inside the circuit. Okay, so that's sort of all the background before we focus on Anonymous Zether. I guess question-wise, we're in pretty good shape. So an overview of Anonymous Zether. It's a privacy token based on partial homomorphic encryption and zero knowledge proof. Those are the two main advanced cryptography used here. Entire state is maintained on chain, but in encrypted format. It's based on a Anonymous Zether protocol. The paper was written by a researcher who used to work for JP Morgan, who was also the researcher who did the implementation of the core library. And this paper was based on the original Zether paper, which was published by Visa researchers along with Stanford researchers. So that's sort of the lineage of this framework. It's a EVM, it can be implemented in many systems, but a EVM-based implementation was developed by JP Morgan originally, and it's owned by, maintained by Consensus right now. A client implementation based on the core library was developed by Kaleido, and I'll be using that implementation for the demo part. So in terms of the technical components that makes it possible, It uses algomal encryption as the encryption scheme, and this was the partially homomorphic encryption scheme that was used, so that smart contracts can do additions and subtractions of the balance in the ciphertext form. For the zero knowledge proof part, it uses signal bullets, which is a kind of bulletproof. So it's not SNARK. It's a different proving system. We don't have time to get into the comparison between SNARK proofs and bulletproof proofs today, but understand that SNARKs is more general purpose. Bulletproofs is better suited for numbers and range types of proofs. For confidentiality, as we mentioned earlier, the encrypted states are maintained on chain so that they are settled by the smart contract. And then for anonymity, every transaction can optionally use an anonymity set. So besides the sender and receiver of the transfer, you can add other parties into this anonymity set as quote unquote noise. And why you are able to do that is you're basically adding an encrypted zero to those other accounts. So they don't care. You're just sending me zero. You're not affecting my my balance. So it doesn't change the state, overall state of the other accounts. But because no one can tell the difference between an encrypted zero versus an encrypted real value, this hides the sender and receiver among the anonymity set. And nobody can tell among these list of parties who's the real sender, who's the real receiver. And if you want to learn more details, you can follow this link and go to the Kaleido page. A little more details on how confidentiality is achieved, and in particular, how we utilize algomal encryption. This is not a new encryption scheme. It's widely used, for example, GNU libraries for PGP encryption. It uses algomal encryption. And essentially what this does is the actual balance to be hidden is hidden in the exponent. So this is doing fairly fundamental algebra, right? Just doing logarithm calculations. You raise a generator number in the curve, in the field to the exponent, and because you are applying the modular operation from the result, you can't revert back to what the exponent is. So that's how the value is hidden. And we're going to show you how this exactly works, but it has the important property of additive homomorphic encryption, as we explained earlier. Okay, so how exactly does this work? So we need to know a few sort of background information, and we may have to zip through this part because of time. G is a special number that's publicly known, and this is selected ahead of time. It's a generator of the group, meaning all the members in this group. It's a group of like large numbers. There are many of them. Every single member is generated by G raised to a power of certain number, and then apply the modulo. So G is considered a special number, and that's publicly known. It's called the generator. And X is my secret key. That's my private key. So, and then public key is calculated as by raising G to the power of X. Let's call it Y. Y is also publicly known. And you can't work backwards from Y back to X. So what I do with my balance is I do this. I raise G to the power of the balance and times my my public key raised to power of a random number. And the result is like this, right? The result is like this. You have the final number as the ciphertext, you know X, you know R, and then as a result, you can work out what B is. But if you didn't know what X is, you can't possibly work out what B is. You have to know X to know B. So that's sort of how you encrypt your balance. Now, how do we do balance updates, right, with these encrypted numbers? So this is based on the formula before, that's your current balance. This is a new balance, and you want to add additional $100 to it or 100 Zether tokens to it. And you are using a new random number or two. So that's one balance, that's another balance. You do the, the basic algebra and you get this. So because R1, R2 are public, Y is public. Then B itself can be public if you know the X. So and then let's use a diagram to go through that. So on chain, let's say Bob's balance is B, and it's encrypted like this off of the map with the key as Bob's public key. Now Alice wants to send Bob 100, right? So she generates R2, uses Bob's public key to come up with this number, send it to the smart contract. The smart contract needs to do this calculation. And this is all possible because all this information is public. So now the on-chain state is updated to this. You still can't work backwards from here back to this number if you didn't have the private key. But if you do have the private key like Bob, then it becomes like this, right? So you know X, you know R1, R2, then you can work out what this latest number is. If you didn't have X, then you can't do this recovery. So that's how this homomorphic encryption with this encryption scheme works. So each transaction looks like this. I have this is the value for the receiver. This is the value for the to be applied to the sender's account minus the value. And this is to be applied to the receiver's account plus the value. And these are the public keys for the sender and receiver, and this is the random number for that transaction. The smart contract will not be able to tell whether the ciphertext here and the ciphertext here represent, minus V n plus V, because you can use any sort of values here, and smart contract can only just blindly apply them. How is the smart contract guarantees that this is a honest transaction, meaning you are giving the same value you are deducting from your own account? And that's where the zero-knowledge proof come in. We don't have time to go through exactly how that's constructed, but just know that it proves to the smart contract that they add up to zero. So no new coins are created in the process. With anonymity, let's say these additional parties A and B besides 1 and 2. So let's say 1 is the sender, 2 is the receiver. We add 2 more as the noise or decoy, A and B. Then you add all of them to the list, and then you list their corresponding public keys in the same order, and they can be processed by the smart contract accordingly. So by now, some of you may have realized there's a potentially concurrency issue because of the necessary coordination between the off-chain state proving versus the on-chain state updates. Let's use some diagrams to illustrate that. Let's say Alice, she wants to send Charlie, which is not illustrated here. She wants to send Charlie $100. Now, she synchronizes her off-chain state with the on-chain state, so both have B. Now, at the same time, and then she goes off to generate her proof, right, based on B. Let's say at the same time, Bob is going to send Alice, let's say $1 or just one token. And let's say Bob also has a faster computer, so he can generate the proof faster and can submit the transaction faster than Alice. Or maybe Bob operates a validator node, and he can control his node to put his transaction ahead of Alice's. What this means is when Bob's transaction gets processed on chain, Alice's balance becomes B prime. It's been updated. So now when Alice's transaction gets processed, her proof is generated based on B, not B prime. So the contract will say your transactions is invalid because you don't have the right proof. Your balance doesn't match. So as long as Bob can keep doing this, or Bob has the ability to control the transaction ordering by operating a validator, then Alice will never ever able to spend her account. So that's a horrible situation we need to take care, right? And this is why Anonymous Zether introduces the pending queue along with the concept of a epoch. So all the incoming transaction balances are put into the pending queue. They're not applied to the accounts balance right away. And they are only settled in the epoch window. Every epoch, at the start of the epoch, these pending queues are applied to the corresponding accounts. And this allows the account owners to spend within that epoch, because within that epoch window, their balances are guaranteed to be not updated by incoming transactions, because again, they get put into the pending queue. We don't have time to go through this diagram. We need to get to the demo. So this is the last slide, and you can go to the Kaleido page that we linked in the previous slide to look at this. Just illustration of how the transaction cycles work with the epoch windows. All right, so let's look at a demo. Kaleido has developed this library called Anonymous Zether client. You can go to Kaleido-io Anonymous Zether client and find this, and then there are tutorials for you to try this out locally yourself. You don't have to use Kaleido platform to accomplish this. But today I'm going to use Kaleido asset platform to show you this demo. So what we have here is I have already deployed the smart contracts involved in the Anonymous Zether flow. There are 4 contracts. This is the top level contracts that our clients will talk to. It uses 3 library ones for the verification of different proofs. And I have already deployed them. So now what we have, so this is, if you're not familiar with this interface, This is Kaleido Asset Platform. There are many services you can use this to manage. You can use it to manage blockchain networks, different protocols. Right now, I have two networks, one for the payments, one for assets. Today, we're only going to use the payments network for today's demo. And it's based on Hyperledger Besu. We have contract management. We have key management. Inside the key management, I provision a HD wallet that we're going to use as sender and receiver as the smart contract deployer. So they are the admin accounts. And we also have Firefly that allows you to look at higher level views, and you can use this to generate APIs. So you can interact with your smart contracts, use it to listen to events. And finally, we have EVM gateway. So this gateway stands in front of your blockchain nodes. So it can be the gateway that send your transactions across multiple nodes so they can share the load of doing the JSON RPC processing. So this is what we point our Anonymous Zether client at. So if we look at the environment, so we have the contract specified, and we have I need to move some of this away, and we have the URL. So let's just start them off. Environment 1, 2. Okay, we start 1. It's very straightforward. It's ready to work now. So now I need to do some renaming. Now I can start number 2 here. Okay, so this is the instance of Alice running on 3000. This is the instance for Bob running on 3001. Okay, so I have all these APIs to interact with Anonymous Zether. First of all, let's see if we've got some accounts. We have some accounts, and they're mapped because of because we need, as explained earlier, we need these special curves inside the circuit. We have to generate new private keys in the new curve, and they both belong to the same identity, right? So I have the Ethereum account along with the corresponding account in the different curve. This is going to be used with the circuit, and I can create new accounts. So I won't do that, as I already got some accounts. So let's check our balance with the ERC20 contract. I have 50. I can mint a bit more, maybe give it another 100. If you have access to the admin account, then you can do that. So now Alice has 150. Let's look at Bob. Bob has its own account, both for Ethereum and for Anonymous Zether. Its current balance is 0 in ERC20, but its current balance is 90 in the shielded account in Anonymous Zether. And Alice has 60. So let's do some transfers between Alice and Bob. Before we do that, we can have Alice convert some of her ERC20 tokens to Zether tokens by doing this funding operation. So I'll fund 100. And this requires a zero-knowledge proof, so it takes a bit longer to generate. So now her balance is increased by 160. So now we can have Alice give some tokens to Bob, maybe give 50. So this is another anonymous Zether transfer that involves zero-knowledge proof generation. You can see it takes a bit longer. So now let's look at Bob's balance. Should be 140, indeed. And finally, some of them may decide that I'm gonna take out some balance from the shielded account back into ERC20. So this step is called withdrawal. When I do that, then this amount is deducted from my shielded balance, which now becomes 90. And then my ERC20 balance is increased by 50. So this is how the entire flow works with Anonymous Zether. You can go freely from clear tokens in ERC20 to shielded tokens with Anonymous Zether back and forth, and you can do transfers in Anonymous Zether with confidentiality and anonymity. So that's the last thing I want to cover today. Last slide is we have the next session on May 9th, same time of the week. All right, and finally, you're welcome to check out Kaleido. All the information about Kaleido, how to use the platform, how to try it out, different offerings are all discoverable on our website. With that, I think I'll stop here.